We've done torque, right?
Mm-hmm.
We have not done torque. Well, that would explain some of the gaps. We're gonna have to come back, and we're gonna have to talk about torque and then come back to this. We usually do torque early on in the chapter. What changed? Torque.
The start of the chapter was when we did the formulas, right?
Yep.
I thought we skipped torque, cause I have a friend in 131. He did torque like a week or two ago, probably a couple weeks ago.
Okay,
So I thought it was like chapter 9.
that's what we're on.
Maybe not. It was like chapter. I don't know.
We're on 9-10. I can't differentiate between the two.
Probably visit later. I don't know.
Did I mention G2 Kabuka?
Yes.
Yes.
I did, okay, so at least I'm talking, oh, that's right, when I put up the chart there. All right, so torque, simple, tau. It is a vector. And the formula,
Oh wait,
so we talked about what affects it, didn't we?
I think we,
Did we get to the equation at stop?
yeah, we just did that force turns into torque, and I think that was it.
That was it.
I think that was it.
Excuse me if I hit you. All right, so think of this as a door. It is open. This is the door, this is the frame. I want it to rotate. I have a natural axis right here. I want this to rotate, since we're talking about rotational motion. What I want to close this as efficiently as possible. How do I do it?
Pull it.
Pull it. Doesn't seem to work particularly well.
You hold it by the end, and you, I don't know,
Pull
drag
it
it diagonally.
Inwards.
Yes.
And bend the door. Drag it that way. It's difficult to drag diagonally because the door's keeping me from doing that.
I don't know, efficient as possible, just hit it on the very end.
Hit it on the very end?
Yeah. Well,
Right.
where you were holding it,
Uh-huh.
we'll just hit it like that. Other way.
There's gotta be a more efficient way of saying that.
Yeah.
Move your hand along the circumference for that.
Along the radius. Radius to the left.
The radius to the left,
Circumference to the left. Circumference to the left.
circumference to the left.
Of the imaginary circle that would be around the axis.
Surely there's a better way of saying this.
Close the door.
All right, so what is going to affect, let's think about the variables involved. What will affect the efficiency of closing this?
The carpet.
Why?
Friction.
Okay, so force involved.
Yeah.
All right, so force has something to do with it. And what else? Why was I told to grab the end or,
So that would be torque.
It's
well,
more
can I
efficient.
close it from here?
Yes, but it takes a lot more
Yeah, a
force.
lot more force.
Okay, so where I apply the force that matters.
Yes.
Oh, that's it. And, well, actually, there's one other thing. So the force matters, where I apply the force, and as was just done earlier, the direction of the force. I need some equation that's gonna bundle all of that together. And we are in luck. There is an equation that does that.
Think about
The simplicity of it all. So, we dealt with dot products, we dealt with work and energy, now we're dealing with cross products. We are multiplying perpendicular components. So if I took an overhead view, that's a door, and with a hinge on the very end like that, and I apply a force like this, so there's my force. R is the moment arm, sometimes referred to as the lever arm. usually call it the moment arm. Some textbooks indicate I would call it the lever arm. It is a vector from the hinge to where the force is applied. Now I need to do a cross product here. Now I've drawn it so that the force is being applied perpendicular to the moment arm, which makes the math simpler. We'll talk about what happens if it's not. So if I'm doing R cross F, if I imagine the two vectors are tail to tail. When I'm doing a cross product, the direction of the answer, because remember, it is a vector product, I put my hand in the direction of the first vector, R. R is going up like that, which means basically my fingers are going to be pointing in that direction. I need to somehow narrow it down. How do I orient my hand? I want my four fingers here to bend so that they bend in the quickest way towards the other force. Since that force is this way, I put my hand like this, the fingers point that way, we'll curl this way, my thumb points in the direction of the product. So if I'm using that convention right there, it would be the magnitude of R times the magnitude of F times K hat. F cross R would go in the other direction.
Magnitude of R times the magnitude of F is equal to K hat?
No, it's in the K hat direction. This would be the magnitude of the torque in this case. And K hat's the direction.
Okay. No.
So in my incredible prop here of a door, if I close this, what will be the direction of the torque that I will need to apply? And how'd you get that? There are a couple ways.
Plus the curve though.
So going with the fact that it's going to move in that direction?
Yeah.
Okay. Since it started at rest, it then moves in this direction. So it goes from zero angular velocity to an angular velocity upwards. That means my angular acceleration is up, which means that my torque has to be up. Or my F forced this way, R is that way, R cross F would be upwards. And I guess those are the two main ways right there. So it would apply an upward torque to the door. Which would probably be the most efficient way of saying how to close that door. That door, also, if I close that door, I have to apply an upward torque. All right, suppose it's not at a right angle. So I got my door right here. And this time I apply a force like that. Figuring out the direction of the torque, same thing. I have R going in that direction. F is going in that direction. R cross F, put my hand in the direction of the first vector, so my fingers curl towards the second one. So R cross F would be out of the board. Supposed to be a dot there. But finding the magnitude's a little bit trickier. Because I really want to multiply perpendicular components. when they were perpendicular already, I'm just multiplying the magnitudes, but if I want to multiply the perpendicular components, well, if this angle here is theta, I need to break one of them up into components. So I'm gonna break force up into a component along the direction of r hat, and then perpendicular to r hat. If I'm doing a dot product, I'm multiplying that length, this yellow length here, along times the length of r. But since I multiply perpendicular, I want to multiply this side times the length of r. And this would be the magnitude of the force times the sine of theta. So generically, the magnitude of the torque is going to be the magnitude of r times the magnitude of F times the sine of the angle between them when they're tail to tail. And if theta is 90 degrees, sine of 90 degrees is 1, and we get back to our first example. How many of you have dealt with determinants? Right. There's a way of solving these with determinants, but I won't bother with that. Alright, so if it's in polar notation, in other words, I can find the angle between them easily, done. Magnitude of one, magnitude of the other, sine of the angle between them. Suppose I give it to you in rectangular form. Or, if I don't drop a syllable, rectangular form. Hold on, there we go. So let's say R is 3I hat plus 4J hat meters. And my force will make -2 newtons J hat plus 5 newtons K hat. There's no reason why I didn't make it three-dimensional. Well, the problem is three-dimensional. There's no reason I didn't make R or F three-dimensional. I'm doing R cross F. I'm gonna FOIL it. So R cross F is, I'm gonna drop my units for now. 3I hat plus 4J hat cross -2J hat plus 5K hat. Now when I'm doing dot products, foiling with dot products, it doesn't matter the order in which it ends up, but cross products, it does matter. A cross B is in the opposite direction of B cross A. So this is going to be, so if I do first, this becomes 3I hat cross -2J hat plus, so that's first outer, 3I hat cross 5K hat, inner plus 4J hat cross -2J hat, plus last 4J hat, not plus, cross 5K hat. I've broken it down, I'm now doing cross products between perpendicular vectors. So I know the magnitude of each of these is just going to be the magnitude of the coefficients there, unless the whole thing is 0. So this will be -6 I hat cross J hat plus 15 I hat cross K hat plus -8 J hat cross J hat plus 20 J hat cross K hat. All you have to do now is figure out what I cross J cross K, J cross J, and J cross K are. Well, let's think about our coordinate system. They're having brown in the upper right corner of the marker board. What would I cross J be?
K hat?
Do it again?
K hat?
How'd you get that?
Didn't you say that earlier?
I did. Suppose you didn't remember, but I said that earlier.
I had a recollection of
Okay, good. Without, because how would you do it if you did not remember? It is the right hand rule. I guess we can just ask Dominic. Might be difficult on a test though. Put your hand in the direction of the first vector. So I is going to the right. I want my fingers to curl in the direction of the second one. J is up, so my hand goes this way. Thumb points out. That would indeed be K hat. This is -6 K hat. I cross K. Put your hand in the direction of the first vector, so your fingers bend towards the second vector.
J hat.
it.
I cross K is not J hat.
Is it still K hat?
No.
Wait, must be I.
Say it again?
It's I then.
Nope.
Okay.
J hat was close.
Negative.
Yes, negative J hat. I is this way, K is out. So hand goes out, right, the fingers curled outwards, thumb points down. So this is -15 J hat. If you want to do 15 negative J hat, just make sure that it doesn't look like it's 15 minus J hat. It's 15 times negative J hat. What about J hat cross J hat?
J hat squared.
No.
Just J hat then?
No. Put your hand in the first vector, so your fingers pull towards the second vector.
I had 0.
It is indeed 0. Remember that cross products are multiplying perpendicular pieces. And if I have two parallel vectors here, their cross product has to be 0. And then J cross K.
I had
So I end up with 20 I hat minus 15 J hat minus 6 K hat. And we're left with what are the units?
meters.
Say newtons or
Meters? Oh wait, oh. Oh, I just realized that.
Think what we
Newton meters?
multiply. Say it again?
Newton meters?
Yes. When we are dealing with working energy, if you get a Newton meter, that is the same as a joule. When you're dealing with torque, a Newton meter is equal to a Newton meter. It is not a joule. In our system, the typical unit would be foot-pound. Although, given the same sequence, a pound-foot, but foot-pound is generally the way it's said. All right, questions? All right, back to here. I'm trying to figure out the torque acting on the wheel. I know that the weight, since I have a natural axis of rotation right smack dab in the middle, the weight exerts absolutely no torque. Because R hat would be 0. It's like trying to open or close a door by pushing on the hinge, directly on the hinge. Generally find it unsuccessful. This normal force holding up the pulley, also, no torque. This force down acting down, that's would basically be pointing towards the center, no torque. Because YR would be this way, or sorry, the force would be that way, the vector would be that way. They are parallel, anti-parallel to each other, the cross product is 0. So the only forces that are exerting any torque on this about the center is Ft5 and Ft4. That would be R, we'll call it R4 and R5. R4 is perpendicular to Ft4, R5 is perpendicular to Ft5. Wow, that's convenient. So our first set of equations here, these are based upon F equals ma. The third equation is going to be based upon the rotational analog, tau equals I alpha. So, basically, it's a k-hat direction equation. I have torque from the Ft5 times R5. That was trying to create a torque, causing it to rotate counterclockwise, which is out. Ft4 is trying to get it to rotate in the opposite direction, so minus Ft4 R4 equals the moment of inertia of the pulley times the angular acceleration of the pulley. Three equations, 4 unknowns. All right, let's figure out what we do now. The weight is easy enough to figure out.